okay? Then how do we do the subtraction? How do we do the feedback, right? For voltage feedback, we just discussed. Can I do feedback by putting two voltage in parallel? Can I do this? So that I can do V1 plus V2? No, right? It doesn't work. This is wrong. It needs to be in series. So what do? We have a common node, and then we will have this feedback going in series with the inputs. This is the input signal. It's not connected to ground. It's connected to the feedback, right? So then let's take a look what it is. Like if I look at this part, I have Z equals to, maybe I should not do this. Let me finish this first. Let's go through the KCL. What is the relationship between V in, VE, and VF using KVL? What's the relationship between V in, VE, and VF? This is V in, VE, VF. What minus? V in minus what? No, just use the KVL. V in minus VE equal to what? VF. Right? Or on the other hand, I can say V in equals to VE plus VF. Right? Because this is a point common, right? Go up by V in, and this is VF plus VE, right? Is that okay? So what is VE? VE equal to V in minus VF. Okay. Now let's compare to this one. VE is Z. V in is X. VF is XF. Okay. That's how we realize the subtraction of voltage. In this sense, right? But how about in transistor? How do we do that quickly and easily? Let's look at this one. What type of amplifier is this? Looks like at least. What type of? Looks like a differential pair, right? What is the gain of a differential pair? GMRD, yes. I say the wrong. Yeah, you're right. You're right. But let's not. I want to say what is V out related to the input. You're all right. This one I give you GMN instead of RD because I'm talking about single-ended. Okay, so this is the equation. So I'm not testing your gain. But what is the right-hand side? What times what equal to V out? This is single-ended. I should have said that it's single-ended. What times GMR N parallel RP equal to V out? V in minus what? VF. Do you agree? Excellent. That helped me to do the voltage subtraction. So what will I do? My input signal I will put here. And then my VF I'm going to put to here. Right? The feedback. Then I realize the subtraction, right? So it's not necessary that I need to put it in series. But actually they are in series. If you really make it into a small signal, I believe this is open circuit, right? And then I do have a voltage source. They are common to the S, right? In some sense, they're in series. I can group them together, actually. Yeah. How about this one? What is the gain of this one? Let's say the current gain. ID equals to what? What is the drain current? How's the drain current related to the gate voltage and source voltage? Drain current, right? How is the drain current related to the gate voltage? What is the magic term? What do you call that? Yeah, you say that already. Either the symbol or... Oh, no. Just tell me it is GM. Yeah. You're right, GM. Yeah, transconductance. You're right also. It's just GM, but GM times what? It's not just VG, right? Times what? Difference of what? No. Sorry, this might be confusing. I'm talking about only this circuit. VG. Very good. VG minus VS, right? Usually VS is grounded. That's why we say ID equal GM right? This is VG, right? So if I call this case 1, this case 2, then for case 1, I have ID equals to GM times what is VG in this case? VF. And what is Vin? So I can do the subtraction on Vin, or in case 2, ID equal to GM times what is VG? Vin, and the other is VF, right? So you have the flexibility to do the subtraction by connecting it to the gate or to the source. Okay? So we are done. So basically, we make sure that now we understand the current must go through both of them, right? And we are able to do the subtraction also. How about current feedback? How do we do the subtraction? Can I do something like this? I1, I2. No, right? Yeah, I know you know it doesn't work. It has to be in parallel. If it is parallel, then I will be able to do subtraction. Using KCL, can you tell me the relationship between I in, IE, and IF? We do it in parallel, right? Here is parallel. What is the relationship between I in, IE, and IF? Just KCL. I in equal to IE plus IF. Very good. Yeah. So what is IE? IE is the quantity I'm interested in, equal to I in minus IF. So this is current. When we talk about this one, we did not say whether this is current or a voltage. As long as you can map to this block, then it still works. What is IE in this case? In the block diagram. Just Z, right? Because it goes into the feed-forward system. And I in is X. Well, how about IF? XF. Do you see that? Yes? First, we did not say whether this is current or voltage. This is just a block diagram. I say I have two quantities, X minus XF equal to Z. I did not say this is a voltage or current. When I do the derivation, I did not say whether it's voltage or current. I get at all the equations without the need to specify whether it's a current and voltage. So now if I can build a system so that IE equal to IE minus IF, isn't that I map to this block diagram successfully? Then isn't that I can reuse whatever I derived that earlier? Okay, and this is just something can be confusing, but I want you to pay attention to, right? How do I do current subtraction in reality? This is one case on the left. The current comes to here. It's supposed to go to the feed-forward. This is feed-forward. But then we have a path to steal away the current. And how do we steal it? Actually, it depends on the gates here. This is going to come out from the outputs of the feed-forward system, right? But we ignore this part. We just say that, hey, this one is equals to IE equals to I in minus IF. Right? That's a way to steal away the current. One single transistor. Another way that we will see very often is this one. We have I in. We use a resistor to steal it away, and this is going to be connected to the output, right? We don't see it, but we still have IE, right? But my question to you is, this is the feedback network. You are doing the subtraction. What should be the input impedance or the output impedance? Because this is the output of the feedback network. This is the output, right? Because this is the input, I sense it, and then this is the output. What should be the output impedance when I do current subtraction? Do you want it to be large or small? Huh? You want to be large. You want it to be infinite. Because I'm outputting remember, I'm stealing the current, right? I'm still outputting the negative current. Remember this. So I'm still a current source. It just that I have a negative current source, right? It becomes a negative current source. So I want to have a large output impedance. What is the output impedance of this guy in what order? Approximately RO, pretty large. So because of this, for RF, should I make it large or small? If I want it to be a good current source to do current subtraction. Large. You want it to be large. A little bit counterintuitive because you think that I want to take away currents, right? If you make it really large, then I cannot take away. But this is a whole system. Other parts will have effect also. So anyway, from this perspective, you want it to be large, okay? And I forgot to say that then for the voltage subtraction, you want it to be small because you are a voltage source now, okay? Okay, so let's stop here.